motivation that we had in mind. Basically, we all know that text applications require semantic inference. Okay, I'm not talking about the grammar checker that may not need semantic inference, but things like question answering, information retrieval, information extraction, all these kind of text understanding applications, they require semantic inference. And right now, or the state of affairs today is that a common framework for addressing applied inference does not really exist. There are traditional approaches of translating meaning to logical forms or such representation as we heard yesterday, the psych approach. But these are really not dominant in the language processing community. If you look at most QA systems, most IE systems out there don't use such approaches. And thus global inference typically is done in an application-specific way. People develop their inference kind of mechanisms in information extraction, in question answering, in summarization. It's done in a quite separate way. While some generic approaches, like for word sense disambiguation, they exist for particular subtasks within semantics, within semantic level, but they don't cover the whole scope, and there isn't much relationship between these isolated subtasks. That's the current state of affairs. And the motivation behind textual entailment is that maybe this is a path to come up with a more principled and a unified framework for doing applied semantics. And if we are after a framework, just to keep in mind, what would you expect from a framework that addresses a certain level of language? The analogy would be in the syntactic level, you have parsing, right? So the framework for doing syntactic analysis is the assumption that syntactic structure should be represented by a parse tree. So the output of a syntactic engine should be a parse tree. The input is a sentence and the output is a parse tree. And everybody that needs syntactic analysis goes and takes a generic parser and plugs it in their application. Okay, so we need a unified task for which we can build a generic module, a semantic engine in this case, that will have clear input-output interface, and it's clear how different applications can use the same output. And then it should also enable us, under this framework, to handle all the different sub-problems. So this framework should enable us to solve word sense disambiguation, name entity recognition, semantic roles, etc., etc. All semantics problems should be embedded. We should be able to address them within the common framework. So that's basically what we need. These are the two desiderata of a framework. Okay. So the outline of my talk, following that motivation, will be as follow. I'll first motivate and define the task. Then I'll talk about the RTE benchmarks. How we set up the data sets and the evaluation methodology, and which systems, which approaches were people came up with to address that. And finally, I'll try to conclude with a broader perspective about this direction and point at some potentials for machine learning. And along the way, I'll try to keep this kind of potential of providing a semantic framework perspective. Okay, so just as a quick glance, why is it difficult? Why is semantic inference difficult? Basically because we are talking about mapping, or we are playing between two levels here. The language level, language is just right, strings if you're talking about text, versus meaning, which we are trying to capture. And very simply, it's difficult because it's a many-to-many mapping, right? Because if it were one-to-one mapping, we shouldn't work hard. Ambiguity is the classical perspective, right? The same language expression can have various meaning, while the dual phenomena is variability, right? Where you can say the same thing in 1,000 different ways. And that's actually why things are difficult. And the textual entailment actually takes a perspective, kind of the focus, the starting point from variability, while it has to encounter ambiguity as well. But it's really the variability of language. When I say variability, I mean the variability of semantic expressions, the many different ways to express the same meaning. That's the real challenge, actually, that I think is faced by text understanding applications. And this is just, to illustrate, we have here a concept, a meaning, right, but many different ways to express them. So let's have a look about the relationship. Let's try looking at the relationship between all these different expressions. So If I want to model the variability of language, I can look at those relations, and the trivial one, the first one that comes into mind is equivalence. Dow climbs 255, Dow gains 255 points are semantically equivalent. And in the more general case, it's a directional relationship, right? Dow climbs 255s, entails Dow ends up, but not vice versa. So the general case is one directional entailment. The more specific case is bidirectional entailment, which means equivalence. Okay, so the question is, can we start focus on capturing this entailment relationship? And what I want to show now that actually capturing this entailment relationship between text fragments is actually what applications, text understanding applications really need to do. So let's take an example for question answering. So suppose you have these questions, who bought Overture? A simple kind of linguistic transformation we know how to do is to transform that to the expected answer form. That's how I call it, the way we'll find the answer in the text. In the text we'll find an affirmative statement of the form X bought Overture. Now if we didn't have the variability of language, we could stop there, right? We'll just look for a string match of some X bought Overture. But the problem is it can be expressed in many different ways, like a text mentions Overture's acquisition by Yahoo, from which we can deduce, infer the right answer, Yahoo. But why is it that Yahoo, we can infer the Yahoo as an answer in this case? That's because this text fragment entails an instantiation of our expected answer, right? Overture's acquisition by Yahoo does entail Yahoo bought Overture, which is just an instantiation of X bought Overture, what we are looking at, okay? So this entailment relation is verifying this entailment relation would actually enable the question answering system to infer the answer. So what we see by this exercise is that actually we can reduce the question answering problem to an entailing problem. Okay, if the question answering had an entailment engine by which it could verify its candidate answers, basically we are done with the needed semantic inference. Okay, and what we were observing that actually a similar reduction, it's a kind of a classical reduction operation in computer science, that you can take many different problems and reduce them to some common underlying problem. So information extraction, I might be interested in X by Y as my target goal, and again I'll need to make the same entailments. In IR, I might have a query like acquisitions by Yahoo, and again, I'll need to make such entailment inferences, etc., in other applications. So this is, if you like, this is the key observation here. That textual entailment is a task to which you can reduce many other inferences needed by applications. So that's the key observation. And this key observation was indeed missing. This is just to illustrate, as an example for an IJCAI 2005 workshop that addressed pretty much the same issues, but under the title of question answering. And it's quite likely that information extraction people or summarization people wouldn't know and wouldn't read the proceedings of this workshop. Okay, so the key goal of textual entailment paradigm is to provide a unified task where all people interested in applied semantic inference, could work under the same framework and collaborate. So if we look at entailment, entailment is a classical notion in linguistics. This is the definition of entailment. So basically T entails H, and we kind of coin these terms of text as the text from which you want to make the inferences, hypothesis, the meaning you want to infer. So basically T would entail H if in every circumstance where T is true, H is true as well. And this is a bit strict definition. The classical one comes from logic or also in formal linguistics, because it really requires that every time in every circumstance, every single circumstance in which T is true, H would be true. So if you'll find some even bizarre circumstances in which T is true but H isn't, entailment wouldn't hold. While it seems that in applied text understanding you want a relaxed version of that. For instance, look at these T and H. Can we infer from T that Ivan Getting invented the GPS? Probably yes, but okay, maybe it was just incubated in his mind and then someone else formally invented it. Okay, so that's what a logician might argue, but we are not after that. If we have that sentence and the question was who invented GPS, we would like to get Ivan Getting as an answer from our system. Okay, so we want to relax it, and relax it as follows. We say that T entails H if humans, so I'll refer to that, so we refer here to human understanding, just in every other NLP task. Reading T will infer that H is most likely true. So it's kind of making the reduction to the behavior we expect from our text understanding systems, right? If I would read the text and infer that Ivan Getting invented GPS, I would like my entailment system to make the same inference, okay? So we see here that it refers to human understanding, and indeed that's the way we work in language processing. We always have humans to annotate our gold standards, just like people decide whether the question can be inferred from a text or not in question answering benchmarks. And we also assume here something else. I don't have much time to elaborate on that, but we assume some background knowledge, right? You know, if I'm saying Bush visited Paris and I ask when did Bush visited France, I assume some knowledge that Paris is in France, okay? So pretty much I'm assuming here common background knowledge, which is what we really expect from our applications or from people that would intelligently make inferences from texts. Okay, so that's the setup. This is the task. Now we have a task. We need some data set for people to evaluate inference method on that. So what was the approach for creating the data set? So the key idea here was to follow this kind of reduction perspective that motivate us at the first place. We said that textual entailment is useful because inferences in many different applications can be reduced to the textual entailment problem. Okay, so let's make this exercise. Let's take real cases of real examples of input-output for different systems. Let's take text messages and answers in QA. Let's take text messages and information extracted by information extraction systems. Let's take documents and IR queries. Let's take examples taken from real application settings, different applications, and transform these examples to the unified format of textual entailment, this text hypothesis format. Then we'll have a unified data set. All examples look the same. For all examples, you have to infer whether the hypothesis follows from the text, but they were derived from data sets coming from different applications. If systems would solve well these inference examples, then it means that the original application could use such an engine to verify its inferences. Okay, so in the first challenge we used these 7 applications. Then afterwards we focused on the first 4. Most data was created from actual input-output. We also kind of improved that along the years. As you can see, the magnitude is not that high, about 800 examples in development and test sets, which means that you can't really expect to learn the knowledge you need from this. This served, as we'll see shortly, it's kind of more of training set for tutors. That's the setup. This is the task. Now we have a task. We need some data set for people to evaluate inference method on that. So what was the approach for creating the data set? So the key idea here was to follow this kind of reduction perspective that motivate us at the first place. We said that textual entailment is useful because inferences in many different applications can be reduced to the textual entailment problem. Okay, so let's make this exercise. Let's take real cases of real examples of input-output for different systems. Let's take text messages and answers in QA. Let's take text messages and information extracted by information extraction systems. Let's take documents and IR queries. Let's take examples taken from real application settings, different applications, and transform these examples to the unified format of textual entailment, this text hypothesis format. Then we'll have a unified data set. All examples look the same. For all examples, you have to infer whether the hypothesis follows from the text, but they were derived from data sets coming from different applications. If systems would solve well these inference examples, then it means that the original application could use such an engine to verify its inferences. Okay, so in the first challenge we used these 7 applications, then afterwards we focused on the first 4. Most data was created from actual input-output. We also kind of improved that along the years. As you can see, the magnitude is not that high, about 800 examples in development and test sets, which means that you can't really expect to learn the knowledge you need from this. This served, as we'll see shortly, it's kind of more of training set for tuning various system parameters. You know, a dozen of parameters, but not, of course, getting the millions of knowledge pieces needed. And just to make it easy to compare to baseline, we took a 50-50 split of yes-no questions. Inference holds, entailment holds or doesn't hold. Which is to remember that the random baseline is always 0.5. So let's see some examples. For instance, the first example was taken from the output of an IE system. It was an IE system trying to identify the located in relationship. And for the text on the left, number 1, it extracted Washington as located in Normandy, okay, which is obviously false. So how did we create the example? The text was a text from which this pair Washington-Normandy was extracted. And as a hypothesis, we just phrased a simple IE statement. Because the relation is located in, we said, okay, we're looking for examples of X located in Y. And we'll plug the X and Y that the IE system extracted. This will give us the hypothesis. If the hypothesis follows from the text, the IE inference is correct. The IE extraction is correct. If the hypothesis does not follow from the text, it means that the IE extraction is incorrect. Okay? So this would indeed provide a false example. Let's look at the third one from question answering. The question was, the original question in the benchmark was when did Cardinal Jesus, etc. died? And the system found the answer 1993 in the text. Again, we made this kind of expected answer hypothesis, plugged in the system answer in the variable place, and again, if this hypothesized answer follows from the text, then this question answer system was right and the inference is valid. Otherwise, not. In this case, of course, humans infer that this is a valid inference. Okay. So this is the type of examples we had. You can see the fourth, that occasionally, of course, you run into examples that are more complex. The last one, if you read it, requires actually mathematical reasoning. And that's not really the focus of let's say, the current, these early stages of the RTE challenges, though people are talking about starting and preparing data sets that would focus on temporal inference, mathematical inference, spatial inference, etc. that are needed eventually. From a good question answering system would know that SPD lost these elections based on the text. Of course, it would require some kind of mathematical reasoning component. Just the final data set to see how the methodology worked, polish the guidelines. So we managed to get quite nice agreements, of around 90% agreement, kappa values of 0.78. That was in the second one, which is actually pretty good relative to semantic tasks, because people, it's amazing when you work on this kind of creating these data sets, how people have different perceptions of language. We just use the same words but have different meanings in mind often. Somewhat different meanings, yeah. Usually 3. And then, of course, to make the data consistent and non-controversial, we excluded those with disagreements. We only kept examples for which there was complete agreement. And here is just an example, right? Does underrepresented mean poorly represented? One annotator assumed it does, and the other. And we also always added a manual filtering stage of kind of things that as organizers, we've seen as problematic. And similar, and you can see it quite converged. Similar figures also happened at the third round. Okay, so methodology quite converged. As you could also see that we could quite smoothly transfer it to select, while it was done in Bar-Ilan originally. Just to give a sense of the progress we made along the years. So one aspect is trying to do this kind of exercise of importing data from real application settings, kind of more rigorous. In RTE1 we still had more of partly synthetic examples. In 2 and 3 the input was quite consistently from common benchmarks. So we took TrackUA and Clay for question answering, and ACE and MAC examples for information extraction, and TrackIR queries and texts TrackIR queries for information retrieval, and then we just let the annotators run them against Google and get relevant and irrelevant documents to extract the text. So we try to simulate quite reasonably the original examples from the actual applications, and we took output of actual applications. So always correct output yielded an entailing example, and incorrect output of the system yielded an incorrect entailment example. Maybe one point to say, and which is kind of a weakness, it's not, I guess it's weakness, so it's not on the slide, but still the examples were picked manually. So the sample cannot be said as being representative from a particular sense. It was more a general guideline of picking kind of a balance of more hard and more easy examples, not too difficult, because as Michel was saying, it shouldn't be too easy, it shouldn't be too difficult. Somehow to aim to the level of state-of-the-art, so it will be relevant for state-of-the-art systems and research. But there's nothing here, a principle to guarantee that. It's more relies on kind of on the intuition of the annotators that pick the examples. We also increased the text length, so at RTE 1 and 2 for simplicity, and also for copyright issues that we kind of managed to overcome through some public resources in RTE 3. Part of the text were extended to a full paragraph, which means you need also to do discourse processing and an aphory. If IBM is mentioned in one sentence, and then it said the company acquired another company in a second sentence, you must make the reference between IBM here and company here to make the inference. And by the way, the 25% proportion was suggested at the end of RTE 2 by the participants. People don't want, another lesson here, people don't want the task to change too much or to become more difficult from year to year. They are still struggling, especially in such a difficult challenge like this. People are still trying to improve the systems, and they don't want the task to get much harder from year to year. Okay, so these were, and you see, data annotation was improved. We also provided linguistic pre-processing, so we parsed the texts for people that are interested. And at RTE 3, we had this resources pool. So Patrick Pantel has set up under the ACL wiki. There is a wiki site for ACL, Association of Computational Linguistics, and within that we have now a resources pool where people put links to various resources relevant for textual entailment. And finally, at RTE 3 is that pilot task that I mentioned before. People from, mostly from US, like from Stanford and from Park, wanted some extensions, and this was eventually run in collaboration between these people that were part of the RTE community and NIST. They kind of got NIST involved, and there were two extensions. One is to provide three-way judgments for the example. So the original textual entailment judgment was, does the text entail or not? While a complete annotation may be, does the text entail the hypothesis? Does the tail contradict the hypothesis? Okay? Or don't know. So this is the three-way judgment. And another was an attempt to asking systems to provide explanations for the reasoning. So this is kind of just illustrates the kind of progress we try to make. Though, as you can see, the basic idea, the basic task, the format of text hypothesis pair remained the same. Just before I finish with the data set, okay, it was a data set, a competition. I never imagined myself before RTE participating in a competition, let alone setting up one. So I was happy to find this quote and put it up in the slides of RTE 1. I think we should remember, and I think also, I was organizing those RTEs, but we were also initiating this paradigm of textual entailment. And what I want to stress, textual entailment is not RTE. Okay, textual entailment is a scientific paradigm. RTE is a specific snapshot to start getting a handle around it, or a uniform way in the community. We apply textual entailment in other applications, in other settings, and just when the next RTE comes, we try to apply our system to RTE. It shouldn't be necessarily the drive. And this is also, of course, RTE has certain drawbacks. Some people